When I was talking about Aristotle, I mentioned his Scala Naturae, the phylogenetic scale. It's really important to not confuse that with the phylogenetic tree. They are two totally different things. The scale versus the tree. A phylogenetic scale is simply a continuum from less perfect or less complex to more perfect or more complex. It's a simple ordering based merely on alleged complexity, the way some people would view complexity. And that's controversial. Complexity could be viewed in all kinds of different ways. It's not something that shows any evolutionary relationships whatsoever. It's simply a convenient ordering. The phylogenetic tree, on the other hand, is historical, meaning it's evolutionary. It's a historical lineage based on data from a whole variety of fields, including, not necessarily limited to, comparative anatomy, paleontology, molecular genetics, and guess what? Behavior. And that's why we're including this short section on the phylogenetic scale versus the phylogenetic tree. Now, Darwin was very keen on all this, and he was fully adopting the phylogenetic tree, not the phylogenetic scale. This is one of his drawings from The Origin of Species, and you can see how there are branches going off, starting way down here with a common ancestor that's branching off, giving rise to all different forms, and there's different branches as you go along. So that's Darwin's phylogenetic tree. And that's basically correct. That's basically what we see today. But, we know a lot more today than Darwin did because we have all these other forms of evidence. And so if you look at, for example, a phylogenetic tree of dinosaurs based on what we know about dinosaurs, it's pretty complex. That's one way of portraying it. Here's another way of portraying it. So these are phylogenetic trees with different branches, as you can see the way these are drawn. Here's a primate phylogenetic tree.
Imagine all life that has ever existed on a giant family tree. From the first microscopic life billions of years ago to all animals alive today. We didn't evolve from modern monkeys, but if you trace our ancestry back in time, eventually we reach a point where the human line and the lines of all primates meet. This is where our story begins, our common ancestor. The ancestor of every monkey, ape, and human alive today.
So again, that's a primate phylogenetic tree, and again, you go back to some common but unknown ancestor. People keep looking, people keep coming up with things, but nobody agrees on anything because the evidence keeps coming in. That's the thing about phylogenetic trees. They are always being revised as new fossils are discovered or different types of analyses are applied to existing items that are available for analysis. So these are never static entities. The phylogenetic tree is something that is always changing as new evidence is being accumulated. You want to see how complex this can be and how daunting a task it can be? You can try this at home. Go to a hardware store and get some pieces of hardware, nails and bolts and screws and all this kind of stuff. And then just scatter them on a table and look at them and try to order them in terms of what you think may have evolved from what. This is one that I did when I was a graduate student. It was an exercise in a comparative psychology class that I took, and my very first class ever in animal behavior. And I thought it was a very clever assignment. So I started doing it in my animal behavior class, the lecture version of the class. Basically, here are just two representatives from two different groups of students. I had students work in pairs, and I provided the hardware. You can see that they came up with very different ways of portraying evolutionary relationships. Look, for example, at what the common ancestor is for these students. Happens to be the most highly evolved for these students. I mean, it's a total flip-flop. So, of course, all we're dealing with this kind of thing is the shape of the objects. And that's why, of course, when you're doing this for real, with real organisms, you're bringing in all kinds of other data, especially DNA, as we'll see shortly. Now, Konrad Lorenz did something rather clever. He had a phylogenetic tree of waterfowl based on their behavior, and this is the way his tree looked. The abbreviations will mean nothing to us because they're basically based on German words. But in any event, each vertical line is a different species of waterfowl. So there's one species there, there's another species there, right on up, and so on and so forth. Each horizontal line is a different type of species-typical behavior. It might be a courtship display, it could be an aggressive display, it could be any kind of species-typical behavior. And what he's done here is portray them in such a way that the dots represent the presence of the behavior in those species between the dots. So in other words, these guys all the way at the bottom perform all of these behaviors. These guys over here only perform those behaviors. So let's just look at this way. So all those guys, all the species in this tree are performing those two behaviors, whatever they happen to be. And everyone in the tree does this, but not geese, because geese are off over there. So they don't do all those other behaviors. And what else? There's the branching off over on the left of wood ducks and mandarin ducks. They have that unique behavior right over here. Again, that's German. I don't know what it stands for. And mallards are up there. And you can see that they do just about most of the behaviors, of course, not the ones that branch off down below, not necessarily at least. So this is just one way of showing how you can potentially use behavior as the basis of a phylogenetic tree. Now, you would never base an evolutionary relationship only on behavior. You would use this in addition to all of the other forms of evidence that I mentioned earlier. Now, here's why it's important to make sure you distinguish between a phylogenetic scale and a phylogenetic tree, because you could end up with very different conclusions, and indeed, if you're using a scale, the wrong conclusions. Fish have swim bladders. Mammals and other forms have lungs. If you were to try to base an evolutionary relationship on a phylogenetic scale, in fact, the word phylogenetic shouldn't even be used here now that I think about it, it would appear that lungs evolved from swim bladders based on our ordering of complexity. I mean, people would generally say that fish are less complex than amphibians, amphibians are less complex than reptiles, reptiles less complex than mammals, and of course I'm missing some groups in between like birds. Anyway, this would be wrong, because if you look at what we do know about the phylogenetic tree involving lungs and swim bladder evolution, so here we have terrestrial males up above that dashed line, some other forms that are not fish that are below that dashed line that are not necessarily solely terrestrial. Here is where the swim bladder evolved, right down there. The swim bladder evolved from lungs, not vice versa. So you can see why it's important to not even attempt to do any kind of evolutionary relationship using the scale, but rather abide by the phylogenetic tree. Okay, what about DNA? Here's a pretty good explanation of the use of DNA in phylogenetic relationships.
In the 19th century, in Darwin's time, it was audacious to claim that humans and chimps were closely related. There wasn't that much scientific evidence. But since that time, the evidence has become strong. First, we saw the fossil record appear. Evidence of human ancestors that had ape-like features established the plausibility of the idea that humans and chimps had common ancestors. And then in the last 20 years, we've seen the emergence of a whole new type of data that's established the close relationship between chimps and humans. And that comes from the analysis of DNA. This is DNA. We've got DNA, chimps have got DNA, bacteria have got DNA, petunias have got DNA, crabs have got DNA. Every living animal, plant, fish, frog has got DNA. And if we compare the DNAs of any two species, we can establish how closely related they are one to another.
In the early days of DNA research, a double strand of DNA was extracted from each species to be compared. When heated, the strands split apart. When the single strands from each creature were put together and allowed to cool, the two always combined to form the familiar double helix. The degree to which the strands mated successfully was a measure of their similarity. It turned out that human DNA and chimp DNA combined almost perfectly. Today, this similarity can be seen even more precisely. DNA sequences can now be read letter by letter.
Here we're looking at the DNA sequences of one particular gene as found in human and chimp. And what's immediately evident is that humans and chimps have DNAs that are 98% identical. They're basically the same. They're just a couple of spelling changes. Why are there only a couple of spelling changes? Because we and chimps had a common ancestor only a few million years ago. And these few spelling differences have accumulated during the propagation of this DNA during those few million years. If more time had passed since we had our last common ancestor, more spelling changes would have accumulated.
If the same gene from a rat is compared, many more spelling differences are seen.
That's because our common ancestor with the rat lived about 80 or 100 million years ago, and there's been much more time for spelling differences to accumulate.
Well, I couldn't have said that any better, so hopefully that makes perfect sense. However, just one caveat. DNA is great. We have a lot of really great data from DNA. But like everything else, you have to exert some caution. It's not necessarily the panacea that's going to give us all the information we need. So here's what can happen. Suppose you're looking at arthropods, and as your representative arthropod species, you're going to look at a tarantula. And you're looking at mollusks, and your representative species of the mollusk will be a scallop. And deuterostomes, your representative species there will be a sea urchin. Okay. If you used the DNA of those representative species, what you would find, based on those spelling errors, is that tarantulas and scallops, in other words, arthropods and mollusks, are more closely related to one another than either of them is or are to the deuterostomes. However, if your chosen species of arthropod is a brine shrimp, you end up with a totally different conclusion based upon DNA analysis, because now what you would find is that the mollusks and the deuterostomes are more closely related to one another than either of them is to the arthropod, using the brine shrimp as an arthropod representative. So you do have to exert some caution, and of course people who do this research know about all this stuff, and they're using other forms of evidence as well, looking at a wider range of species from each group, not just relying on a couple chosen species, to figure out what the evolutionary relationships are in the phylogenetic tree. So again, the scale goes all the way back to Aristotle, but if you're interested in learning anything about evolutionary relationships, then you deal with the phylogenetic tree.